In this video, we're going to be taking a look at pipe fill calculations according to Section 12 of the Canadian Electrical Code, and specifically we're going to be referencing 12-910 for how we do that. So let's get started. First kind of question that has to come to mind when you're talking about pipe fill is how full can any particular raceway be? Because that ultimately will dictate the number of wires of any particular size that we can pull into that given size of raceway. And 12.910 gives us guidance on this by referring us to Table 8 of the codebook. Now, unless you're talking about a scenario where you're pulling in one or two conductors or cables, max pipe fill is 40% for non-lead sheathed conductors or cables. And what that means is that for the majority of scenarios in which you're going to be doing a pipe fill calculation, you're going to be talking about a scenario where it's going to be a maximum pipe fill of 40%. So if you're ever stuck, you got no way of knowing how to proceed, you've totally forgotten where to look in the codebook, just keep in the back of your minds, and this applies to out in the field too, you're looking at max pipe fill, generally speaking, of 40%, which means that when you look at a raceway, like the one that I'm kind of illustrating here, if you were to imagine that 40% of that raceway is that much volume, that means that when you now look at any given bundle of wire, in terms of the total area that that bundle of wire occupies, that has to fit within that 40% of your given raceway size. So the next question that comes up, and this is often because people get confused between pipe fill questions and ampacity questions, is students or individuals even in the field will make statements or ask questions about whether or not neutrals or bond wires get counted when we're doing pipe fill or box fill. And the reality is that when you're talking about pipe fill as opposed to ampacity, you're concerned about physical space. You're not concerned about the heating effect of current flow as you are in ampacity calculations. Here you're talking about just the physical space occupied by a conductor. So because of that, if you think about the question, do we count neutrals and bonds? Well, it becomes very obvious. Absolutely you count neutrals and bonds, because at the end of the day, a bond wire, even though it doesn't carry current, it absolutely occupies space, and therefore you have to count it when you're doing pipe fill calculations. Same thing with neutral conductors. A neutral conductor doesn't necessarily carry a significant amount of current, as in the case of a balanced three-phase four-wire system, but it does occupy space, so it has to be counted when we're doing pipe fill. So the next question that arises is, how do we actually determine appropriate pipe fill for any given scenario where you have to put a certain bundle of wire inside a raceway, a conduit or a piece of tubing, and now you need to determine what size tubing you actually have to run to house that bundle of wire. Well, what we have to do is we have to start by calculating the total amount of space occupied by the conductors within that raceway. And the way we do that is by looking at the cross-sectional area taken up by each individual conductor, and then adding all of those cross-sectional areas together to get a sense of the total cross-sectional area that the bundle of wire occupies within the raceway. So let's try that out. So you might come across a question that's just asking you to look at the cross-sectional area of a bundle of wire, and then it gives you the parameters for that bundle. So you're told that you have 4 number 8 conductors, and those are RW90 XLPE, so that's the insulation type, 600 volt rated, it's unjacketed, and it's stranded conductor. Then you've got 8 number 6 conductors that are T90 insulation, nylon, and they're also stranded. And then you've got lastly 6 number 10s, and those are TW75, also stranded. So what you have to do then is you have to go to the appropriate table for those cross-sectional areas, and as I mentioned in the previous slide here, those tables are tables 10A through 10D. 10A being for stranded, 10C being for solid conductors, and those two are really the two that we use most often. So in this particular problem, because all of our conductors are stranded conductors, what we're going to do is only use table 10A. What we do there is we go into the table and we first use the information about what kind of conductor we're using to locate the appropriate column to use. So you'll notice that in your table 10A, the first type of conductor is the R90, RW90 XLPE, 600 volt unjacketed. And if you go and look in table 10A, that is your very first column after your wire sizes in the table. How do you know that it's unjacketed? Because in the table it will just say RW90 XLPE 600 volts. Well, the way you know that that first column is for unjacketed conductors is because of the little asterisk that is beside XLPE. If you go and look at the bottom of this table, you'll notice that that asterisk is associated with unjacketed conductors. So we use the first column for our wire type, but then you'll notice that underneath this wire type there are 2 subcolumns. One is the actual diameter of the conductor, and the other is the area. We don't care about the diameter. That is irrelevant to us. We care about the physical space that it occupies. Therefore, we always look at the area of the conductor in millimeters squared. So, having located the correct column for your wire type that you're looking at, and then making sure to use the area subcolumn, you simply go down that column until you intersect with the wire gauge that you're looking at, which in our case, for our first wire type, is number 8. So we go across at number 8, intersecting with RW90 XLPE 600 volt unjacketed, and we get a cross-sectional area of 28.17 for that particular type of wire. So I'll go and write this in here, 28.17, and that is obviously going to be multiplied by the 4 conductors of that size that I have going into that raceway. You do the same exact thing for each of your other types of conductor that you're looking at pulling into the raceway, and what you end up with is a scenario whereby you've gone and identified the individual area of each of your different wire types. So here we have our XLPE R90 or RW90, then we've got our T90s and our TW75s. And we don't care when we're doing pipe fill that these have different temperature ratings for the insulation on these 2 or these 3 different kinds of wire. We don't care about that from a pipe fill point of view. We do care about that from an ampacity point of view. But here it's just physical space, so who cares what the insulation is, other than the fact that it dictates the size of the conductor itself. So, having located the individual cross-sectional area of your different wire types, and then having multiplied it by the number of that type of wire that you have, which in our case was 4 of the RW90s, 8 of the T90s, and then 6 of the TW75s, making sure to use brackets here, all you have to do then is just add those areas together. So this is just a summing calculation where we take them and just add them all together. And what you get there is a sum total area occupied by the bundle of 468.38 millimeters squared. That's your sum total area. In other words, if you were to look back at this notion that we have to fit a given bundle of wire into 40% of whatever raceway we choose, 40% of the cross-sectional area of that raceway, what we've now determined is that our bundle of wire is this 468.38 millimeters squared, and now we need to match that to a raceway that is sufficiently large. Now the way that we're going to do that is we're going to go to the tables within the Canadian Electrical Code that give us the cross-sectional areas of various types of raceways at various percentage fill. And so when we take a look at tables 9A through 9H of the code, we see that that's exactly what these tables do. They give us various percentage fill values for various types of raceways that we may encounter in industry. Now, what I will say about these tables is that if we take a look at table 9G, 9G gives us the 40% pipe fill cross-sectional areas for the vast majority of raceway types that we will come across on a regular basis in industry. Table 9H is also for 40% fill, but it's for much more specialized and rarely used forms of raceway. So if there's one of these tables that we're going to use on a regular basis, it'll be table 9G. And again, if we're pulling anything more than 2 conductors or cables through a raceway, we are required to go to a maximum of 40% pipe fill. And so that's why I say table 9G, which is 40% pipe fill for the majority of common raceway types, that's going to be our most often used table out of this range of table 9A through H. Now what we're going to do when we take a look at table 9G, we're going to see that on the far left hand side of this table we've got rigid metal conduit, all the way through to the right hand side where we've got electrical non-metallic tubing. And then just to the left of electrical non-metallic tubing, we've got EMT. And so in this problem, we're looking to try to find the minimum size EMT that we could install to deal with this bundle of conductors that we've just calculated. And so how we do this is we take a look at our bundle of conductors, which has a cross-sectional area that we've just calculated of 468.38 square mils. Then what we're going to do is go down the 40% fill column under EMT, and we're going to look for a number that is equal to or greater than our calculated bundle cross-sectional area. And when we do that, we come to this number of 515.3. All we have to do then is go across in that row and see that this is associated with trade size 41 EMT. And we can be confident because this trade size 41 EMT has a cross-sectional area of 515.3 square millimeters at 40% fill, that we will be able to fit our bundle which was only 468.38 millimeters squared, into this raceway. Now, the reality is in industry we would most often refer to these raceway sizes as an imperial value, for example 1 inch or 3/4 inch, rather than trade size 27 or 21 respectively. And so, having calculated our trade size 41, we may want to actually put this into an imperial value. Well, that's easy enough if we remember that at the front of the codebook in the preface we're given a conversion table, and so we can flip to that conversion table and very quickly conclude that this trade size 41 is the equivalent of 1.5 EMT. And so that's as simple as it is. We calculate the bundle of wires cross-sectional area, and then we simply come to table 9G and select the appropriate column for the type of raceway we're using, and then we just go down until we get to a number that is equal to or greater than our calculated bundle cross-sectional area, and that's the size we would select. So let's try a full problem. You might get a question like this that says, what's the minimum size of rigid steel conduit that can be used to pull in the following conductors? And then you get your list here. So you get 6 number 4 R90s, 600 volt unjacketed stranded, 4 number 8s that are TWN 75. Careful, because in these pipe fill questions, one of the problems or one of the mistakes people make is quite regularly when you get a TWN conductor, a lot of people drop the N mistakenly and go and get their area off TW75, and therefore you get, in most cases, the question wrong. So be very diligent when you're doing your actual areas per conductor, that you're doing it for the appropriate wire type that you're actually getting in the question. So we've got these 4 number 8 TWN 75s also stranded. You've got 8 number 6s. They are RW90. These ones are 1000 volt insulation, unjacketed stranded, and then you've got 1 number 8 R90 600 volt unjacketed stranded bond wire. So in this case we're told that it is actually a bond wire. So then the question, again, as I mentioned before, sometimes because people are thinking about this incorrectly, they're so used to doing ampacity problems that they say, oh well, I'll just drop the bond wire because I don't need to include the bonds. Well, this is about physical space, so you absolutely have to include the bond wire. It's taking up physical space, so you have to count it. So what you're going to do then, as we've already talked about, go to table 10A. All of the conductors in this question are stranded. There's no mixing of stranded and solid here, so we just use table 10A. Go down your table 10A, selecting each of your appropriate areas per conductor, and again, be very careful, be diligent that you are using the area column. The other most common mistake people make in these pipe fill questions is that where you're looking in table 10A and you've got 2 subcolumns per wire type, people will make the mistake when they're doing pipe fill questions of using the diameter column, and that's just bad juju. You're going to get the question wrong for sure. What you have to do is keep in mind that realistically the diameter columns are pretty much useless to us for when we're doing these calculations. What we have to be doing is using the area columns. So you could even go ahead and highlight your area columns all the way down so that you know whenever you're doing pipe fill, you're only using the area. So because you've been diligent, you've paid attention, you've done it correctly, you've gone and now selected all of your areas for your different wire sizes. Again, it's a very simple process then at the end. If you've put brackets around everything, you can just do all of this in your calculator in one step, bracket everything, order of operations, and then just simply add it together, and you will get a grand total area for this bundle of wire of 811.41 millimeters squared, or square millimeters. So having now found the size of the bundle that we're going to be using, or pulling in, we now need to go and choose an appropriate raceway size for this bundle of wire. And so in this example, we were asked to figure out the minimum size of rigid metal conduit that would be able to hold this bundle of wire. And so we're going to go to table 9G. We're going to be looking at this table because it covers 40% pipe fill for these various types of raceways that we use on a regular basis. And the very first group of columns is dedicated to rigid metal conduit. And so with this calculated bundle of 811.41 millimeters squared, we're going to go down the 40% fill column under rigid metal conduit, and we're going to be looking for the first number that is equal to or larger than our 811.41. And when we do that, you see that we eventually come to 879.48. And if we go across that row to the left, we'll see that this is associated with trade size 53 rigid metal conduit. And we can be confident now that with trade size 53 at 40% fill, giving us 879.48 millimeters squared of cross-sectional area, our bundle, which is only 811.41 millimeters squared, can easily fit within that 40% fill. And thus we can be confident choosing trade size 53 for this problem. Now once again, to put this into imperial, which would be more commonly used on site, we would just simply go to the preface and see that the conversion means that trade size 53 is 2-inch rigid metal conduit. Now from here, let's do a little bit more of a complicated problem. So this time, we're wanting to know the minimum size of core line that we're going to be able to run in order to house a particular bundle of wire. Keep in mind that core line, you won't find that in the codebook. That's like a brand name. The codebook refers to core line as ENT, or electrical non-metallic tubing. So that's your core line in the codebook. Now, the other tricky thing about this is the way that we're given the information about our conductors, which requires us to build on our our trade knowledge, as you were. So we're told that we've got two 3-phase 4-wire sets of number 8 AWG T90. Well, what you have to be very diligent about is not thinking that you've got two number 8 conductors, because that's incorrect. You've got two sets, and those sets are each a 3-phase 4-wire set. In other words, each of those sets has a red, a black, a blue, and I don't have the ability to draw a white line, but I'll put gray for our neutral. So the reality is now, when we consider a 3-phase 4-wire set, you've got to keep in mind that you're then talking about 4 conductors per. Okay? So be very diligent when you're reading questions to make sure that you're understanding the full scope of what they're actually telling you. So again, just making sure that everybody is 100% squared away on this. When you look at a 3-phase 4-wire set, you do in fact have neutrals involved. If I go back to this one here, you can see a 3-phase 4-wire set is your 3 hots, red, black, blue, phase A, B, C, and they share a neutral. And of course, because of the fact that it's a 3-phase 4-wire set, that neutral is a true neutral, and it would only ever carry the unbalanced current from these 3 line conductors. So because of the fact we have neutrals involved, true neutrals, sometimes people get confused and they start saying, well, I don't have to count the neutrals for a pipe fill question. Well, that's absolutely incorrect, because we're talking about physical space, not the heating effect of current. So for physical space, for pipe fill questions, you absolutely count the neutrals. So based on that then, how many conductors do we actually have to be concerned about? Well, for our first line of information, because we've got 2 3-phase 4-wire sets, that means we actually have 8 of these conductors, 8 number 8s, which are T90. Now you'll notice that this particular one does not say whether or not it's stranded or solid. However, if you go to tables 10A and 10C, what you will notice is that 10C, which is for solid conductors, only goes up to number 10 AWG. And that's because they don't make it in solid conductor above that size. So they don't make number 8 solid. It would be simply too stiff in order to be used for any real effective installation. Hence, over the threshold of number 10, it's guaranteed to be stranded. If you were given a question where it included number 10 wire or number 12 wire that is left blank, you're not told whether it's stranded or solid, the safest thing to do is to assume that it is stranded and go from there. Now, moving on with this particular problem then, we've got 8 of these T90s. Our second bit of information was that we had 3 of these 3-phase 4-wire sets of number 10, and so that gives us a total of 12 of those wires. But be careful, these ones, it is telling you that they are solid. Same thing for our third row of information. So we've got these 4 single-phase 2-wire sets of number 12, and again, also specified as solid. And then lastly, we've got our number 10 solid bond wire. And of course, we count the bond wire because it takes physical space. When you go to table 10A, for our first bundle of wire here, you'll get a 23.66 millimeters squared per, and then you're going to use table 10C for the remainder, because all of the remaining conductors are specified to be solid conductors. And you're going to get 13.25, 10.02, and then another 13.25. All you have to do then is put all of this into your calculator, adding them all together, and you're going to get a grand total or sum area of 441.69 millimeters squared. And that is your area that that bundle takes up. So what we have to do now that we've got the cross-sectional area of our bundle of conductors is we have to go to table 9G, because again we're going to be looking at a 40% fill, and table 9G has all of the most common raceway types in it. And in this case we've been asked to find the minimum size electrical non-metallic tubing, which is basically core line, that would be able to hold this bundle of conductors that we've just calculated. And so considering that we are looking at a bundle which has a cross-sectional area of 441.69 millimeters squared, we want to go to table 9G, go and look at the 40% column for electrical nonmetallic tubing, and then we're going to go down that column until we reach a number that's equal to or greater than this 441.69. And when we do that, we see that the next greatest number is 491.91. When we go to the left along that row, we see that that is associated with trade size 41 ENT. And once again, if we wanted to convert this into an imperial value, we'd go to the preface and we'd see that this is again 1.5 inch ENT. And so, simple process. Once we've got our bundle cross-sectional area, we just go to the appropriate column in table 9G, go down that column for the raceway type we're using, and select a raceway based on a cross-sectional area that is equal to or greater than our bundle cross-sectional area. And then we can be 100% confident that our bundle will fit in that raceway. Now the very last thing we're going to talk about to do with pipe fill is we're just going to answer this question of what are tables 6A through 6K used for. And the reality is I'll just preface this by saying tables 6A through K don't necessarily ever have to be used. You can do the vast majority of calculations just as effectively using the process that we've looked at so far, taking your cross-sectional area of each individual type of conductor from table 10A or 10C. But table 6A through K might help perhaps to add a little bit of speed to the process, although frankly I would argue that they might actually be slower to do it this way. Nonetheless, how do they actually get used? Well, what they've done is they've taken the various types of conductors in terms of construction and placed them into an individual table where then they've given cross-sectional areas of not just one conductor, but of bundles of that same type of conductor of various sizes. And so, for example, if you get a question where you need to size a raceway for being able to hold 10 number 8 AWG conductors that are all R90 600 volt unjacketed, then what we can do is we can use table 6A to go and get the cross-sectional area of that whole bundle of 10 conductors, rather than going to table 10A and getting the cross-sectional area of one of those conductors and then multiplying it by 10. So if you ask me, it's a little bit redundant, but nonetheless that's how the table works. So what we would do, go to table 6A, and we would look for the intersection of number 8 as a row and then the column that is associated with 10 of these conductors. And when we see the intersection of those two values, the column of 10 and the row of number 8 AWG, we see that this bundle would have a combined cross-sectional area of 281.8 millimeters squared. And so you could do this where you look at a problem like the one we just did, where we've got a bundle comprised of several different groups of conductors, and we could go and get the cross-sectional area of each of those groups from your tables 6A through 6K. But frankly, like I said, in my opinion, it's not particularly useful, and I recommend you stick with the steps that we've shown in this video over the previous couple of examples. So with that takes care of our video on pipe fill.